Friends, how are you? Welcome to my YouTube channel Enlightened Mind. Today we will be calculating the capacitance of capacitors, and the main focus of today's lecture would be essentially towards the parallel plate capacitor. But before that we need to have set a relationship between the charge and the potential. So let us student try to understand that suppose we have considered, suppose there is a particular sphere, okay, and this is a particular sphere which is a conductor having a radius capital R and has some charge on it, some suppose positive charge, and that positive charge is Q. Then we know that the potential of this capacitor at the center O would be 1 upon 4 pi epsilon naught Q divided by capital R. Okay, electric field at the center is 0, but the potential is this. Okay, and this potential would be same from 0 to the surface of this sphere. Okay, that is spherical conductor. Okay, so now suppose this spherical conductor has some capacitance, and we know that this charge is directly proportional to V. Okay, so if suppose this, by seeing this relation, you can say this Q would be 4 pi epsilon naught into R into V. So we have taken all these terms except Q on the left hand side, so we get this Q is equal to 4 pi epsilon naught R into V. And if suppose Q is directly proportional to potential, that we know as the charge of this particular sphere would increase, potential would also increase. And so if you replace this proportionality sign, you will get a constant, and that constant is C. This C basically is the capacitance. Capacitance of any conductor or a particular body can be defined as the capacity to hold the charge. Okay, so that basically is the ability or the capacity of a particular conductor or anybody that could hold a particular amount of charge. So that particular capacity is called the capacitance. Okay, so here this, if you'll compare these two equations, here this one and second equation, then you will know that C, which is the capacitance, would be 4 pi epsilon naught into capital R. So here this capacitance of a spherical conductor having a charge small q would be equal to 4 pi epsilon naught into capital R. Okay, so that is the capacitance of the spherical conductor. Right. Okay, so now we will consider a particular case. Okay, we already know that if suppose we have a charge sheet, okay, and that particular charge sheet has a particular amount of charge, that charge suppose is small q, okay, and another sheet is there, and this sheet would have another charge suppose minus q, that is minus q. Okay, so we have three kind of region. One is this, another second is this, and third region is this. Okay, and suppose we consider that this particular sheet is infinitely long, okay, that has an infinitely long area. So the electric field at any of the point would be sigma upon 2 epsilon naught. Okay, so where this sigma is the surface charge density. Okay, surface charge density, which you can write is Q divided by total area of this particular parallel plate. So at this particular region, suppose that it is the region 1, so these are the two plates A and B. So electric field, because of E, because that is the positive charge, should be away from that particular sheet, and that should be in this direction. So that is the electric field due to A. Okay, similarly, if you try to calculate electric field in first region, because of this negative sign, that would be towards this, so that should be in this direction. So electric field here should be EB. Okay, So the electric field in first would be, and suppose here the of that particular electric field of this particular A sheet, suppose is sigma 1 upon 2 epsilon naught, because I considered that the surface charge density of A plate is sigma 1 and surface charge density for this particular sheet is suppose sigma 2. Okay, so so electric field because of the plate B would be sigma 2 divided by 2 epsilon naught. Okay, so electric field at the first region we have calculated here is that the electric field B in the positive direction minus electric field in the negative direction, right? So just you need to subtract these two. So here B1, B is basically sigma 2 divided by 2 epsilon naught, and here this is this one which is sigma 1 upon 2 epsilon naught. So you can take 1 upon 2 epsilon naught common, so that would be sigma 2 minus sigma 1. Okay. Similarly, suppose I will consider this region second, so that second region would be in this direction and this would also be in this particular direction. Okay, the electric field here should be away from E, away from this positive charge from A and towards B, that is the electric field due to A, electric field due to B. Okay, so the electric field in the second region should be EB plus EA. Okay, so that should give me 2 epsilon naught sigma 1 plus sigma 2. Okay, so likewise electric field in the third region could also be calculated. So because of this positive, that should be away from A plate, that is electric field due to A, but here because of B, which is in the negative sign, should be in this direction, so that is the electric field due to B. Okay, so now you can write that this should be electric field due to A minus electric field due to B. I am taking this positive because that is in the right direction and it is in the left direction. Okay, so anything which is going right, I am taking it as positive, and in the negative, I mean on the left hand side, I am taking it as the negative one. Okay, so that should be 1 by 4 pi epsilon naught. This time EA is basically sigma 1, so you can write sigma 1 minus sigma 2. So that is the electric field. Now suppose I have considered a special case here, and I already said that this particular suppose sheet is of charge plus q and there is minus q. So let us consider that sigma 1 is equal to plus sigma, which is surface charge density having charge plus q. Similarly sigma 2 is minus q. So in that case you can see here that the E1, because this sigma 1 sigma 2 is of negative sign, okay, or all are positive, so you can see that that particular thing would be cancelled out. Okay, and here it should be subtracted, right? So in that fashion you can say that the electric field in region A first and in region third would be 0, and electric field in the second region, because that has become positive all the way, so that would be sigma 1 and that is sigma 2. So that should be sigma and that is also sigma, so that would be 2 sigma divided by 2 epsilon, so that you can write sigma upon epsilon naught. So that basically is the electric field, okay, of a uniformly charged sheet where one is positive and other is of negative surface charge density. Okay, so by using this identity we will calculate the electric potential between these two plates, and then we will find out what is the capacitance of this parallel plate capacitor. Okay, so let us consider that the potential we know that the electric field is minus dV upon dr. Okay, and suppose these two parallel plates, suppose these are the two parallel plates, okay, and this distance between these two plates, which is dr, is suppose is d. Okay, that is the distance. So and this dV, the potential, electric potential or the potential difference between these two plates, suppose is V. Okay, so this expression can be written as capital E is equal to V upon D. Okay, So the potential would be minus E and D. So that can be written as minus sigma epsilon naught into D. Okay. And suppose I am interested only to find the magnitude of this potential, so the negative sign would go and only positive sign sigma epsilon naught divided by epsilon naught into D would come. Okay, so that is the potential of parallel plate capacitor, and that then we know that that would be potential is nothing but Q, okay, upon C, because V is equal to Q is equal to C into V. So that is the C, Q by C, or in other words you can write that C is equal to Q upon V. So you can write you can put this value Q, and V is sigma upon epsilon into 2 D that we have already calculated. One thing also we know that the sigma is surface charge density, which is Q by A, so the Q can be written as sigma into A. Okay, so you can put this value here, so that would be sigma into A, okay, and that is sigma, epsilon naught would be here and D is here, so sigma would cancel out, so only you can write that C, which is the capacitance due to a parallel plate capacitor, would come out to be A epsilon naught divided by D. Okay, so that basically is the capacitance of a parallel plate capacitor, okay, having an electric field, suppose E, okay, which is dV by dr, and then by calculating the value of V, we can find out the value of C, because we know that the C is Q upon V. Okay, so now let us consider, so that basically is the parallel plate capacitor. Okay, so if suppose I have a parallel plate, and that parallel plate is this one, okay, and this has some area, and area, suppose this is the area, which is A, okay, and the distance between these two plates is D, then the capacitance would be sigma epsilon naught A upon D. That is the capacitance of parallel plate capacitor. Now suppose I have inserted a particular plate here between the parallel plate capacitor, and that plate can be conductor or an insulator, or you can say a dielectric slab. Okay, one thing we need to consider here is that the conductor has an electric field inside it as 0, while the insulator or a dielectric has a net electric field, and that net electric field is not 0. It simply means that if I'll put a particular, suppose that is a insulator or a dielectric, and if I'll put this insulator in an electric field, suppose that is the electric field, so there would be an electric field inside the conductor, which is EP, that is called electric field due to polarization. Due to polarization of the molecules of that insulator or dielectric, such that the net electric field is not 0. Okay, but here in this case, conductor is, suppose I have a conductor, okay, and if I'll put this conductor inside an electric field E, then what happens is that the electric field inside the conductor is in such a fashion that EC is equal to E. Okay, means the electric field inside the conductor is equal to the external field. Okay, so in that fashion you can say the electric field or the net electric field of a conductor becomes E minus EC, and because this E and C is same, so that would be 0. So you can say that the electric field inside a conductor becomes 0. Okay, But why is such? Because we know that electric field goes from positive to a negative direction. Okay, so when I put a conductor inside an electric field, so all the positive or the negative charges comes at this edge, okay, where the positive charge of electric field is there, and the positive charge would be along or towards the negative. So an electric field from positive to negative direction inside the conductor would set, and this intensity or the strength of this electric field is equal to the strength of this one, because inside an electric, because in a conductor there is no, you can say, um, electric field, or you can say the electrons inside a conductor is plenty in number. Okay, so the electrons, okay, or the negative charges inside the conductor set themselves in such a position or in such a configuration that they set an electric field equal to the direction of the external electric field. But here in this case, you can say in case of an insulator or a dielectric, there the electrons are not freely available. Okay, and it means that the atoms or the molecules inside a dielectric can slightly change their direction, but they effectively is not able to completely isolate themselves, or you can say cancel out the external electric field. Or you can say here the electric field of an insulator becomes E minus EP. Okay, but that is not zero. Why it is not zero? Because electric field due to polarization is slightly less than the electric field of external field. Okay, and that electric field you can say is the net electric field, or you can say simply E. Okay, and that basically is the electric field E naught divided by K, and this K is basically is the dielectric constant, or you can say ER. You can say there is an electric field due to medium, okay, medium divided by electric field due to epsilon naught, which is the because of the vacuum. So that is relative permittivity, or you can say the dielectric constant, which is ER. Okay, that you can easily find out, and why this has come, that also we know. Suppose the electric field, okay, when there is only vacuum, and that electric field is E naught, so its value is 1 upon 4 pi epsilon naught, that we know. And electric field, suppose, is because of Q, and the distance is R square. Okay, and suppose there is now I have a particular medium. Okay, I have put a particular medium, and that medium when electric field is passing through it, so it has an electric field inside this one, and that is electric field due to medium. So electric field due to medium is 1 upon 4 pi epsilon naught is become epsilon m. Okay, and that is also Q by R square. Okay, because here the medium is different, so the electric field exerted or experienced by that medium would be different from the electric field experienced by a vacuum. Okay, so when you divide these two quantities, you will have E naught divided by EM, everything would come cancel out, and only EM epsilon m epsilon naught will remain, and that I define as relative permittivity, or epsilon r, or I can say it is equal to K. So essentially you can write the electric field due to medium would become E naught divided by K. Okay, so that is why I have written over here that the electric field due to medium, which is E, is equal to electric field due to vacuum divided by dielectric constant, which is K. Okay, so it means that if I'll put a particular suppose I have I kept a particular conductor inside the parallel plate capacitor, then I need to calculate what is the capacitance of the capacitor, parallel plate capacitor having a conductor inside it. Okay, so I'm now calculating it. So the my now task is to find the capacitance of parallel plate capacitor having a conductor or conductor slab inside it. Okay, so that is my task. So now let us consider that this is a particular parallel plate capacitor having some thickness which is small d, okay, and area, and that area is, suppose, is capital A. There is the area of this this particular slab, okay, which is A, let us, and I have put a particular for the sake of simplicity I am putting this slab here, okay, just adjacent to this particular plate, okay, and suppose this thickness of this conductor is small t, okay, obviously this then would become d minus t, okay, and I already said the electric field inside this conductor is 0, but here the electric field is same, which we already calculated, which is E naught, that we know, and E naught we know is we know what is this, sigma upon epsilon naught, that we know, okay. So now our task is to find what is the capacitance of this particular plate. So first of all we calculate the potential, and we will calculate the potential due to conductor plate or conductor slab, and then plus potential due to vacuum, okay. So we know that potential is electric field into distance, okay, and the electric field of this slab is suppose E, and thickness is T, which is the distance. Similarly for vacuum, electric field is E naught, okay, and distance of this vacuum now has become d minus t, and there is no more d now. That is that because out of this d, small t is used by the conductor slab or the conductor. So in this case we know that the electric field due to conductor is 0, so that would just go only electric field due to this E naught, t minus t would remain, and that we know that this is nothing but sigma upon epsilon naught, that is d minus t, okay. So now our task is very simple, so just we will calculate what is C. C is nothing but Q upon V, and Q is sigma into area, and V is nothing but sigma, and that is d minus t, and this epsilon naught would come in the upper side, so that would become A epsilon naught d minus t, okay, very simple, okay. So it's suppose we consider a number of plates, conducting plates, okay. So suppose this particular slab, okay, this is suppose is the parallel plate, okay, parallel plate capacitor, and we have a number of slabs here now, okay. Suppose that is the slab having thickness T1, then there is another slab, okay, having a thickness suppose T2, and then another slab having thickness T3, and so on and so forth, and all are conductors, right? So we know that now C, effective C, which is the capacitance, would become then A epsilon naught d minus, you can write then T1 plus T2 plus T up to Tn, okay. So that would become actually the capacitance. So likewise, suppose capacitance parallel plate capacitor having a conductor, not a conductor but a dielectric slab now, that we will calculate. So let us consider another example. So now our task is to find what is the capacitance, okay, of parallel plate capacitor having, you can say, dielectric slab, right? Inside it. Very simple. So now suppose we will consider that here there is a parallel plate capacitor, and now we have put a particular slab which is dielectric, and then we know that the electric field here is, in this case, would be E naught divided by K. Okay, and that is the parallel plate. Its area is A and the distance is D, and thickness of this particular dielectric slab is T. So obviously the area of that particular space where there is no dielectric, there is only vacuum, would be D minus T. Okay, very simple. So in this case, electric field, again our task would be to find out what is the potential. So the total potential we know is the potential due to dielectric slab, okay, plus because of the vacuum, and that we know that the electric field due to dielectric slab, electric field and its thickness, plus electric field because of vacuum and its thickness, which is D minus T. Okay, so that we will calculate. So that can be written as E naught divided by K T plus E naught D minus T. Okay, or you can write simply it as E naught T by K plus D minus T. Okay, so this E naught we know is sigma upon epsilon naught, and that is T by K plus D minus T. Okay, now you can write that this C will be Q divided by V, and what is sigma into A, which is this Q, and V is this much, which is sigma epsilon naught, and that would come in the denominator. Epsilon would be here, and that would be T by K plus D minus T. That's all. Okay. So sigma would cancel out. That can be written as A epsilon naught T by K, then plus D minus T. Okay. Now suppose consider that there are a number of slabs. Okay, dielectric slabs. Suppose a number of dielectric slabs are there. So one is having K, one dielectric constant, and having thickness T1. Another slab, suppose, is having a dielectric constant K2 and has a thickness T2. Similarly, some other, this suppose is having a thickness T3 and K3 is the capacitance zone, and this is the parallel plate. Okay, suppose that is the, and this particular thing is covering every area. Okay, so that area is A, that we know, and the thickness of this plate is D. So the capacitance now would become A epsilon naught divided by, so that is for only a particular dielectric slab, and now there are n number of dielectric slabs. Okay, so the expression would now become T1 divided by K1 plus T2 divided by K2 up to n, Tn divided by Kn. Okay, and then plus you can write D minus T1 plus T2 up to Tn. So that would be the capacitance, expression for the capacitance of a parallel plate capacitor having a number of dielectric slabs. That is for first only for one dielectric slab, and that is for a number of dielectric slabs. Okay, so I hope this lecture would be very helpful, and if you like this lecture, you can click on the like button and subscribe my channel if you hadn't done it yet. Thank you for watching my video. Thank you very much.